So we're going to look at some exponential growth and decay problems where we can you studied exponential growth and decay in pre-calculus, but now since we know how to take the derivative of exponential functions, we'll be able to look at some of these growth and decay problems from where we involve calculus. So remember that the general model for all exponential growth and decay problems is given by some form of this equation. Like you might see different variables used. I'm using a of n is equal to a sub 0 times the quantity 1 plus r raised to the n power, where a of n is the amount, the number, the population of concern. And I'm using function notation here. You don't have to use function notation, but just to show that the amount, the number, population of concern is going to be a function of the number of periods that have occurred and number of periods. And remember back to when we were reviewing exponential functions, and we kind of talked about exponential growth and decay. The intuitive definition is that a quantity is either increasing or decreasing by a common percentage per period. So we're raising 1 plus r to the nth power. N represents the number of periods that have occurred. And we can define what a period is depending on what units we're using. Okay, so the constant a sub 0 is going to be the initial amount or the initial population. So basically, whenever no periods have occurred, what is the starting amount? And then the constant r is the rate of growth or decay. And we represent r as a decimal or a fraction. Whenever we're talking about growth, so a quantity increasing in size, then r is going to be a positive decimal. And if we're talking about a quantity decreasing, then that would be representing exponential decay, and r is going to be negative. So I give the examples like 7% growth per period can be written as r equals to 0.07. 65% growth per period would be r equals to 0.65. 150% growth per period, so over 100%, would be 1.5. And then decay examples. So 20% decay per period would be r equals to negative 0.2. And then there's the special cases. So whenever we talk about a quantity doubling every period, that means 100% growth. So r would be equal to 1. Tripling per period is actually 200% growth. So r would be equal to 2. And then oftentimes when we're talking about radioactive decay, in which half of a substance decays per period, that means that r is equal to negative 0.5 or negative 1/2. So in the case of radioactive decay, the period actually has a special name. It's referred to as the half-life of the substance, and we'll do some half-life problems. And observe that all cases can be handled with the same equation, which is cool. Sometimes we find it more convenient to express a as a function of some variable t representing the amount of time passed. So whether we want to represent time in seconds, minutes, hours, days, weeks, months, years, rather than just having a be a function of the number of periods that have occurred. This can be done. So to do this, we're going to pick a unit of time that we want to measure t in, and then we need to relate n and t. So meaning we need to figure out what the relationship is between a period and that unit of time, so that we can then substitute in for n the expression that involves t. This is more so that you don't have to figure out in your head or as side work the number of periods that have occurred. I have an example here. So if we have some population that starts at 40 and grows 20% every 15 minutes, then the initial amount, A sub 0, would be 40, R would be 0.2, and N would be the number of 15-minute periods that have occurred. So instead of having to think, well, okay, if 30 minutes have passed, how many periods have occurred, which that would be 2 periods, we can figure out the relationship between N and T. So in that case, N would be equal to the number of the number of minutes that have occurred divided by 15. So if T is in minutes, T divided by 15 would be the number of periods. And then we can rewrite our equation. If we wanted T to be in hours, like you could use different units for time. If we wanted T to be in hours, you could think, well, in 1 hour, 4 periods would occur, right? 4 15-minute periods, because 60 minutes divided by 15 would be 4 periods. So the way that we could relate the number of periods in time where time is in hours is N would be equal to 4 times T. And we could write our equation in that way so that we can plug in number of hours that have occurred, or like let's say it's a fraction of an hour, then that just makes it a lot easier than having to on the side figure out the number of periods that have occurred. So generally we can do whatever is most convenient. So either stick to working in terms of the number of periods N, or pick a useful unit of time for that specific problem and then express everything in terms of T. Now there are 2 formulas that are kind of special cases, but they're still based off of this general model. So the first one is compound interest formula. In this formula, we're usually talking about money. So let's say we have a principal amount, so an initial amount is invested at an annual rate that is compounded multiple times per year, so N times per year. Then the amount in the account at the end of T years is given as A equals to A sub 0 times the quantity 1 plus R over N times N to the T power. Very similar to that general formula. The thing is, you're given an annual rate, but you're given that it's compounded so many times per year. Like if it were compounded quarterly, that would be 4 times per year. You would actually divide the rate by 4 to figure out what the actual rate of growth is per period. And then to come up with the number of periods that have occurred, well, like if T is, let's say, in years, so let's go back to thinking about is growing at some rate that's compounded 4 times per year, compounded quarterly, then you would do 4 times T to represent the number of periods that have occurred. So 4 times the number of years that have passed. And the annual interest rate is expressed as a decimal, just like R was represented as a decimal before. So if you deposit $10,000 into a savings account that earns 3.5% interest per year compounded, let's come up with the model for these different amounts that the interest is compounded. So for yearly, since we're given an annual interest rate, right, 3.5% interest per year is what the savings account earns, that actually means that the interest will just be applied once per year. So N would actually be equal to 1 in this case, and we could actually just use that general formula from above. So $10,000 being our initial amount, we would have 1 plus 0.035 raised to the t power, and t, I'm going to use years. So t is the number of years that have passed. Okay. Monthly, well, we're given the annual interest rate is 3.5%. So it makes sense to do our input, t being in years. Monthly, well, there's 12 months in a year, so that means the interest would be compounded 12 times in 1 year. So our initial amount is the same, but we're going to end up dividing 0.035 by 12 and then multiplying t by 12. And t is still in years. Weekly, there's 52 weeks in a year. So same initial amount. Now we would divide 0.035 by 52 and then raise to the 52 times t power. T is in years. And then for daily, let's say that there's 365 days in a year. So the interest is applied 365 days per year, but it's not 3.5% every day. It's whatever 0.035 divided by 365 is applied each day. And then the next special case is where if we think about taking this formula where we're compounding the rate n times per, in the definition up here we have an annual rate compounded n times per year, but it could really be as long as the units match up, like what the rate represents with the unit of time. So let's just say that we have, we're given an annual rate that is compounded infinitely many times per year. Well, we can't plug infinity in for n. So we can use this formula. So continuous compound interest formula. And this formula isn't just used for money. It can be used for any quantity that is going to be continuously increasing or decreasing. Like populations, we could think of as being continuously increasing. So this formula can also represent population growth or decay. So if a principal a sub 0 is invested at an annual rate compounded continuously, then the amount A in the account at the end of t years is given by this formula. This comes from taking the limit of the above formula. You remember limits? So the limit as n approaches infinity, right? Because we're thinking about compounding an infinite number of times, of a sub 0 times 1 plus r over n to the n times t power. And I'm not going to actually show the work to getting to this formula, but that's what we end up with. So a equals to a sub 0 times e, right? So e, remember, is approximately 2.71. It's Euler's number raised to the r times t power. And again, the annual interest rate is expressed as a decimal. So if $10,000, if you deposit $10,000 into a money market account that pays 2.3% interest per year compounded continuously, the equation that could represent that would be A equals to 10,000 times e to the 0.023 times t power, where t is in years. Okay, and we can actually come up with continuous growth decay equations for all exponential or most exponential growth and decay situations. we just have to solve for the annual rate based on R being compounded continuously. Like if we go back to like, let's say we go back to this situation. So if we deposit 10, well, no, that one would be too easy. So let's do something else. So let's go back to this example. And I'm going to take this equation, which represents a population that starts at 40 and grows 20% every 15 minutes. And the equation that I'm using has t in minutes. Okay, so we could actually come up with a different equation that has base e, so that's in this form, but we would need to solve for what the rate would be for continuous growth, right? This is talking about population growth. So what we could do is let's find the population after 15 minutes have passed. So after one period has occurred. So A of 15 is 40 times 1.2 to the 15 over 15th power. Well, 15 over 15 is 1. So after one period has occurred. I'm not gonna simplify this. I want the exact value. I'm gonna use that as the population. So 4 times 1.2 to the first power equals to that initial population. And then if I use the e to the r times if 15 minutes have passed, we're going to solve for the rate. So it would actually be not the annual rate. It would be the rate per minute, but representing continuous growth for the population. So if we, I don't know why I wrote 4. So if we divided by 40 on each side, we would be left with 1.2 equals to e to the r times 15th power. And then to solve for r, let's rewrite this in logarithmic form. So that's 15r equals to natural log, right? Because log base e, the base is e, of 1.2. So r would be equal to ln of 1.2 divided by 15. So the equation would be a equals 40 times e. R is natural log of 1.2 divided by 15 times t. And t is still in minutes. And you could confirm that these equations are equal to each other by graphing. So basically they have the same inputs and outputs. If we did that on Desmos, if I type in y equals 40 times 1.2 to the x, I'm using x instead of t, over 15th power, okay? And then if I type in the other equation, so y equals 40 times e to the, I'm going to use parentheses here, so ln of 1.2 divided by 15 times x. Okay, so I don't know if you saw that. but those two graphs end up overlapping each other exactly. Okay, so let's look at some examples. So let's say you deposit $1,000 into a savings account that earns 3.8% per year. Okay, we're going to write a mathematical model to represent the amount of money in your savings account as a function of time. Okay, so we can use whatever letter we want to represent the amount of money that's in the savings account. Like I could use S. The amount of money that's in the savings account, we put an initial amount of $1,000 in. The savings account, the amount in there is going to be growing as interest is applied. So it'll be 1 plus the rate of growth, the growth rate, 0.038. And then it's interest per year. So we can actually just use, one period is going to be 1 year. So we can just do T in years. Okay. So if we want to know how much money would be in the savings account after 7 years, we could just plug in 7 for T. And we get approximately $1,298.32. Okay. And how long would it take for your money to double? Well, if we started with $1,000, for it to double would be the amount in your account being $2,000. And we would be wanting to solve for how long, so how many years have passed for that to happen. So notice if we divide by 1,000 on each side, we get 2 on the left side. Okay, and then from here we can rewrite in logarithmic form as T equals to the log base 1.038 of 2. That's the exact value of the amount of time it will take for your money to double. If you type that into your calculator, you get approximately 18.585 years, or approximately 19 years. You could always round that up to be approximately 19 years. This kind of yucky looking thing, that's the exact value. That's actually the doubling time. That's how long it takes for your initial amount to increase 100%. So part D, question D says, using part C, write a different equation that models this situation. So since we know how long it takes for our initial amount of $1,000 to increase 100%, we actually know the doubling time, and we can write our equation with the same initial amount, is it 1,000, sorry, not 10,000. And then using that 100% growth rate, so R being equal to 1, and then T, so let's think about it. The number of periods that would have occurred for 100% growth rate, like if we want T to be in years, we would have to divide T by how long it takes for our money to double, to increase by 100%. So we're going to do T divided by our doubling time, log base 1.038 of 2. Okay, so this equation, which we could do 1 plus 1 is 2, So 1,000 with the base of 2 to the t over log base 1.038 of 2, okay, where t is in years. And you could double check that that equation represents this situation by graphing the equation that we just came up with in part D and the equation in part A, and they would match. Now part E, here's where calculus is coming in. So at what rate in dollars per year is your savings account earning after 5 years? So what that question is asking is, at that moment in time, so after 5 years, at what rate, like in dollars per year, is our savings account increasing? So this is asking for the instantaneous rate of change, which means we want to take the derivative of one of our equations. I'm going to take the derivative of the first equation that we came up with. Because it's just a little bit simpler than the equation that we came up with in part D. So S prime will be 1,000 times 1.038 to the t power times natural log of 1.038. Remember, the derivative of a to the x power is a to the x times natural log of a. So if we want to know what the instantaneous rate of change is in dollars per year after 5 years, we'll plug 5 in. And I get approximately $44.94 per year. Okay, and then we're asked, what's the rate after 10 years? So we'll plug 10 into the derivative. And we get approximately $54.14 per year. And what about after 15 years? What's the rate? So if we plug 15 in, okay. So notice that we can clearly see that the growth is not linear. It is not the same rate each year, in dollars per year at least. Because this is exponential growth, where the amount that you have is increasing by a percentage every period, or in this case, and every year is increasing by 3.8%. We can see that the rate is actually increasing. And that makes sense if we were to look at the graph of this equation. So y equals 1,000 here. I'm probably going to have to zoom out a lot. 1,000 times 1.038 to the x power. There it is. So that's even in the negative. So we have the initial amount of 1,000 that we put in, and you can see that the steepness of this graph, that the amount of money starts increasing pretty quickly from that $1,000. So the slopes of the tangent line end up getting steeper and steeper and steeper, meaning that that rate, that instantaneous rate of change, so the rate of increase in dollars per year, is going up and up and up. Okay, so let's look at our next example. So let's say you buy a new car for $35,000. The value of the car decreases by 20% each year. This is called depreciation. So our model, let's use C to represent the value of the car. It starts at $35,000. Okay, the value is decreasing, so R is going to be negative or minus 0.2 in our equation. And then we'll still do, one period is 1 year, since it says 20%, decreases 20% each year. So we can still do T in years. How much will your car be worth after 2 years? So we can plug 2 in for T and get approximately $22,400. So after 2 years, the car is worth $22,400. So a lot less than what you bought it for. And that's true about cars. Cars decrease in value really quickly. Okay, part C. How long will it take for your car to be worth half of its initial value? You might call this the half-life of your car. Okay, well, if it starts at $35,000, half would be $17,500. And we're solving for that time. If we divide by 35,000 on each side, we'll have 1/2 equals to 0.8 to the T power. So T equals log base 0.8 of 1/2. That's the exact value. That's approximately 3.106 years. Okay, so using part C, we can come up with another equation that models this situation. So we know how long it takes for the car to decrease in value by 50%. So we could come up with the equation using that half-life. Okay. It takes approximately 3.106 years. So if we still want our input to be number of years that have passed, to figure out the number of periods that have occurred, you would take the number of years that have passed and then, or how old your car is, and then divide it by that half-life. So divide by log base 0.8 of 1/2. And then if we want to know how long it will take our car to be worth $10,000, we can set one of those equations equal to 10,000. Okay, and then if we divide by, if we divide by 35,000 on each side, we get 2/7 equals to 0.8 to the T power. So T equals log base 0.8 of 2/7, which is approximately 5.614 years. Okay, if we want to know at what rate in dollars per year is your car decreasing in value after 2 years, 5 years, 10 years, we are being asked the instantaneous rate of change. So we need our derivative of our equation for C. I'm going to use that first equation that we wrote. So C prime would be 35,000 times 0.8 to the t power times natural log of 0.8. And to find what the rate of change would be after 2 years, we'll plug 2 in. And I get approximately negative $4,998.42 per year. Remember, it's a negative because the amount is decreasing. The value is decreasing. To find out for 5 years what the rate would be, plug in 5. Now, knowing that the value of the car decreases 20% every year, that does describe a rate to us. But if we want to know, like, at one particular year, how the value is changing in dollars per year, that's where we would use our derivative. So after 5 years have passed, the value of the car is decreasing at $2,559.19 per year. Okay, 10 years. I get negative $839.59 per year. Okay, so what does it seem like is happening to the rate? So it actually seems like the rate is slowing down, or the car starts losing less money per year the older that it is. So if the car is decreasing, that should make sense. So if the car is decreasing in value, like the graph of our equation that represents the value is going to be decreasing, right? It represents exponential decay. So the curve kind of ends up, as time is passing, ends up flattening out more and more and more. So your car ends up losing less and less money each year, but it's also worth a lot less than it started with. Okay, so I pulled data the other day on COVID-19. So this has changed. Like whenever I looked at it yesterday, the data had already, like the doubling time for number of confirmed cases had already increased, which is a good thing, right? It had already gone up to 7 days. So the data is constantly changing. It's very hard for doctors and the people that are studying this to come up with a mathematical model for this. But we do know that the number of cases worldwide as well as in the United States has grown exponentially. So on April 5th, 2020, there were 312,237 confirmed cases of COVID-19 in the U.S. Based on data published by the European Center for Disease Prevention and Control. And the number at that time, the number of cases was doubling about every 6 days. So that means that the number of cases is increasing 100% every 6 days. So we can use, I'm just going to use A as the number of confirmed cases. I'm going to use that amount on April 5th, the 312,237 300,237 as my initial population. Okay, increasing by 100% every 6 days. So like after 6 days, we could think of one period having occurred. After 12 days, 2 periods. So if I want to do t in days, I'm dividing t by 6 to come up with the number of periods. So t is actually days since April 5th, 2020. Okay. So from this model, how many confirmed cases would we predict there to be on April 7th? Well, April 7th is 2 days later. So we would plug 2 in for t. And we get approximately 393,000. I'm having trouble talking. 394 cases approximately on by April 7th. From that same model, at what rate, so in cases per day, is the number of confirmed cases increasing on April 8th? So we would find the derivative of our model. Okay, so that would be A prime equals to 312,237 times 2 to the t over 6 power times ln of 2, and then thinking chain rule. Because t over 6 is the inside function here, we have to do times 1/6. April 8th is 3 days after April 5th, so we'll plug in 3 for t. And when we do that, we get approximately 51,012 cases per day. Which again, this has already changed. We know that the doubling time in the United States has already increased. So this is just based off of that one, the model we came up with. So if the number of confirmed cases continues to double every 6 days in the United States, how long would it take for there to be 1 million cases? So we take our model, set A equal to 1 million. Okay, divide and then rewriting in logarithmic form, we would have t over 6 equals to log base 2 of 1 million divided by 312,237. We multiply by 6. And that is approximately 10 days. Okay, and just kind of to comment on the situation, that's why there's the social distancing and the not being in school and everything that the government has come down with, is to try and slow the rate of spread for COVID-19 down. So that's why these numbers are not actually accurate. So the doubling time back on April 5th was approximately every 6 days. But again, because there is intervention, and there's also some error based on like how tests are being performed, like availability of tests, that also affect the numbers. Okay, so let's see. Do I want to do these? All right, so number 4. There was a zombie outbreak in your town. The number of zombies increases by 42% every 3 days. So I'm going to use Z for number of zombies, or my zombie population. Let's say that the zombie population, or assume it starts with 1. And the population is increasing 42% every 3 days. So if we want time to be in days, so after 3 days, 1 period would have occurred, right? That percentage is based on every 3 days. So number of days that have passed divided by 3 would represent the number of periods that have occurred. So where T is in days. So how long would it take for the number of zombies to quadruple? So basically, how long would it take for us to have 4 zombies? Okay, so T over 3 equals to the log base 1.42 of 4. And then if we multiply by 3 on each side, I get approximately 11.86 days. Okay, using this model in calculus, what rate in zombies per day is the zombie population increasing after 1 week? So after 7 days have passed, what is that rate of change? So we're going to take the derivative, which would be 1.42, so the T over 3 power times natural log of 1.42 times 1/3, because you have to think chain rule. And then when we plug in 7, I get 2.265 zombies per day. Okay, so not even a whole zombie each day. Remember, this is just to model data, to model a situation. It doesn't, obviously you cannot have 0.265 zombies. Okay, so over the first week, on average, how much is the zombie population increasing per day? So this is referring to from that first day to 7 days later. On average, how much is the zombie population increasing? So this is actually asking for average rate of change, which remember is the change in Y, or it would be the change in the zombie population divided by the change in X, which would be the change or the number of days that have passed. So the zombie population after 7 days would be 1.42 to the 7/3 power minus the initial amount, which is just 1, the initial population, but I can plug 0 in for T. And then 7 minus 0. If I type that in, I get 0.181 zombies per day. Okay, and for why are the rates so different? Part C is asking for instantaneous rate of change, and part D is asking for the average rate of change. So we know that our equation for Z, well, I don't know why I used A. It should be Z. Z prime. Okay. So our equation for Z, the zombie population, represents exponential growth. So it's a curve that kind of looks like a J. Okay. If we are asking for the average rate that the zombie population is increasing, well, that would be saying, what is the slope of the line that passes between these 2 points? This first point representing the initial population, so the population on day 0, and then the second point would be representing the population after 7 days. And then by dividing the difference in those populations by the number of days that has passed, that tells us on average how much the population was increasing each day that happens over the week. And that ends up being the slope of this line. Remember the slope of the secant line. Versus part C was asking for how fast the population was increasing on day 7. So that would be the slope of the tangent line. So that's instantaneous rate of change. Which is the slope of the tangent line to the curve for t equals to 7. Okay, so this is our last example. Let's say we have a 100 gram sample of an unknown radioactive substance. After 24 hours, 32.9 grams of the substance remains. So we aren't given a rate here, but we need to come up with the model. So we need to use the given information to actually solve for the rate. So we know after 24 hours, there's 32.9 grams left of the substance. So let's say that 1 hour is a period. Yeah, so we're going to solve for the rate of decay per hour. So if we divide by 100, that would be 0.329 equals 1 plus r to the 24th power. And then to get the 1 plus r by itself, we can raise both sides of the equation here to the 1 over 24th power. So we would have 0.329 to the 1 over 24th power. Okay, and I can actually stop there. I don't need to keep going because remember, we don't know, we're really solving for the base. So our equation could be A equals 100, and then 1 plus r is 0.329 to the 1 over 24th power. Okay, and then to the t power is t in hours, which if you're raising a power to a power, that can also be written as 100 times 0.329 to the t over 24th power, where t is in hours. If we want to solve for the half-life, that would mean how long does it take for our initial amount of 100 grams to decrease to a 50 grams. So if we divide by 100, we get 1/2 equals to 0.329 of t to the t over 24th power. Rewriting in logarithmic form, and then if we multiply by 24. And I get approximately 14.964 hours. But this would be the exact value for those number of hours, or the exact half-life. So we can actually write another equation where we know, since we know how long it takes for our initial amount to decrease 50%, okay, for that rate, one period is approximately 14.964 hours. So if we still want our input to be in hours, we do t divided by our half-life. Where t is still in hours. Okay, and then for at what rate is the substance decreasing after 6 hours have passed? So that for that rate, what we're referring to is grams per hour. So after 6 hours, what's that rate? And then 10 hours, 30 hours. So we want to find a prime. I'm going to use the first equation we came up with. So it would be times natural log of 0.329 times 1 over 24. And then we can plug in 6. And I get negative 3.508 grams per hour. It's negative because the amount is decreasing. For 10 hours, plugging 10 in for t. I get approximately negative 2.915 grams per hour. And then for 30 hours, negative 1.154 grams per hour. And it seems like that rate is slowing down. So it seems like the instantaneous rate of change is decreasing, is slowing down. So the amount is getting smaller and smaller as time is passing, but with each hour that passes, there's less and less, meaning it seems like the curve is leveling out. And we know that since this equation represents exponential decay, right, the curve is going to be decreasing kind of like that, and you know that then the curve levels out, the slopes of the tangent lines become